Welcome, everyone. If you're a university math student grinding through real analysis, you know exactly how overwhelming these theorems can get. Well, take a deep breath क्योंकि आज हम इस particular topic को बिल्कुल break down करने वाले हैं. This right here is your ultimate study guide for the Riemann Stieltjes Integrability theorem, specifically focusing on the sum of integrable functions. हम इन handwritten notes के हर एक step को bilingually simplify करेंगे ताकि the whole concept becomes absolutely crystal clear to you.
Okay, let's just dive right into this. Our final destination for today's explainer is actually a beautifully simple idea. Simple शब्दों में कहें तो अगर हमारे पास दो functions हैं, say f1 and f2, और दोनों एक same function alpha के respect में Riemann Stieltjes integrable हैं, तो उनका combined sum यानी f1 plus f2 भी integrable होगा. और सिर्फ इतना ही नहीं, the integral of their sum will be exactly equal to the sum of their individual integrals. That is our goal for today, the final finish line we are running towards.
So here's our roadmap to tackle this without any stress. First, key notations and setup. Second, deriving the basic inequality. Third, proving the integrability. And finally, proving the integral formula. Let's get to it.
All right, part one, key notations and setup.
Honestly, keeping these variables straight in your head is half the battle won. So P is our partition from A to B. Delta alpha I, now this is absolutely crucial, it's greater than or equal to 0 क्योंकि हमारी function alpha strictly increasing है. फिर आते हैं हमारे bounds. Capital M is for the upper bound and small m is for the lower bound. एक single prime is for f1, double prime is for f2, और जो बिना prime वाले हैं वो हमारे sum function f के लिए हैं. And obviously we have the standard formula for upper and lower sums. Just lock this vocabulary in your mind.
Moving right along to part two, deriving the basic inequality, covering steps 1 through 3.
Step 1 is basically laying our foundation. We start by assuming f1 and f2 meet the integrability conditions, which inherently means they're bounded. I mean, logic dictates that if two separate things are bounded, इनका sum f भी to bounded ही होगा, right? Exactly. फिर step 2 में हम अपना partition P introduce करते हैं, and we just formally define the bounds for each subinterval like we saw in the notations.
Now, what I really love about this slide is how cleanly this table organizes all that heavy algebraic notation from the original text. आप यहाँ easily देख सकते हैं कि f1, f2 और हमारे sum function f के अपने infimum मतलब lower bounds और supermum यानी upper bounds हैं. It's basically a clear, easy-to-read map of who is who.
Okay, pay attention here क्योंकि यहाँ से real magic शुरू होता है. This is our key inequality. The infimum of the sum, that's mi, is always greater than or equal to the sum of the individual infimums. And similarly, the supremum of the sum, mi, is always less than or equal to the sum of the individual supremums. This is a massive algebraic stepping stone for us. दोनों functions के bounds हमारे sum function को tightly एक defined limit के अंदर pack कर देते हैं.
Let's scale this up across the entire interval. Step 3 uses a very classic mathematical analysis trick. हम अपने inequality के हर एक term को delta alpha I से multiply करते हैं. And remember what we said earlier? Delta alpha I is always non-negative, 0 या उससे बड़ा, तो हमारी inequality का direction बिल्कुल change नहीं होगा. Then we just seamlessly sum it all up from I equals 1 to n.
And the result of that trick? This absolute master equation, the basic inequality. Just look at how the lower sums of f1 and f2 are teaming up to set the absolute floor, while the upper sums are setting the ceiling for f. Dosto, literally star-mark this equation in your notes right now, because this is the engine driving the entire rest of our proof.
Okay, section 3, proving the integrability, which takes us through steps 4 to 7.
We are making great time. Welcome to step 4, home of the very famous epsilon by 2 trick. क्योंकि f1 और f2 दोनों integrable हैं, we know that for any positive epsilon, we can find partitions where the upper minus lower sum is strictly less than epsilon. But check this out. We intentionally split epsilon right down the middle, making it epsilon by 2, ताकि बाद में जब हम इन्हें add करें, they perfectly snap together into one whole epsilon. Then in step 5, हम बस इन partitions P1 और P2 का एक common refinement, जिसे हम P कहते हैं, वो ले लेते हैं.
So the real light bulb moment happens right here in step 6. जब हम अपना u-l calculate करते हैं for our combined function f, using that basic inequality we starred earlier, we can break it apart into the individual upper minus lower sums for f1 and f2 separately. Or क्योंकि हमने वो clever epsilon by 2 trick use की थी, it directly gives us strictly less than epsilon by 2 plus epsilon by 2, which mathematically is exactly epsilon. Boom! Integrability criterion completely satisfied right there in step 7.
Take a quick second to appreciate this actual snippet from the handwritten notes. By Theorem 2.2, we've essentially nailed the first huge chunk of this. Hence, the sum of two Riemann Stieltjes integrable functions is again integrable. Give yourselves a quick pat on the back. We are officially past the halfway mark and doing great.
All right, final stretch. Part 4. Proving the integral formula, steps 8 to 10.
Time for the final boss. We already know the sum is integrable, but now we actually have to prove the integral of the sum is exactly equal to the sum of the individual integrals. In step 8, हम वापस अपनी basic inequality पर जाते हैं और उस partition P का mesh size shrink करके 0 की तरफ ले जाते हैं, essentially passing to the limit. Limits apply करने पर, our upper and lower sums morph into proper integrals. लेकिन एक छोटी सी catch है. Limit pass करने पर हमें less than or equal to का relationship मिलता है. Let's bookmark that and call it result 4.
Now, here's a fun little puzzle for you. हमारे पास less than or equal to तो आ गया, but basic logic dictates that if A is less than or equal to B, and A is also greater than or equal to B, then A absolutely must equal B. So the big question is, हम will reverse inequality, यानी greater than or equal to, कैसे लेंगे? Any guesses? सोचो ज़रा.
This right here is why math is so incredibly cool. Enter step 9, the negative trick. हम completely flip the script और अपने functions f1, f2 and f को strictly उनके negative counterparts से replace कर देते हैं. Replace किया और वही same result 4 इस पर directly apply कर दिया. The genius part, जब आप equation के दोनों sides को -1 से multiply करते हैं, the negative signs vanish और rules of algebra के हिसाब से inequality का sign violently flips from less than to greater than or equal to. Boom! That gives us result 5.
Step 10. Hence proved. Result 4 gave us less than or equal to. Result 5 just gave us greater than or equal to. The absolute only mathematical reality left? Perfect, exact equality. और इस तरह से हमारा formula solidly, without a doubt, prove हो जाता है. The integral of the sum, truly, exactly, is the sum of the integrals.
Before we wrap this explainer, let's lock this entire proof into your memory with a rapid-fire English cheat sheet. Number 1. F1 or F2 bounded हैं to sum completely bounded hoga. Number 2, our key inequality bounds the sum. Number 3, delta alpha is always positive, क्योंकि alpha strictly increasing here. Number 4, always grab that common refinement P. Number 5, the legendary epsilon by 2 trick is what controls both functions. Or number 6, perfect equality चाहिए, just hit the whole thing with the negative trick.
जाने से पहले एक quick thought experiment मेरी तरफ से आपके लिए. Throughout this entire proof, हमने इस assumption पर heavily rely किया कि delta alpha I is greater than or equal to 0, simply because our function alpha was strictly increasing. But wait, what if alpha एक strictly decreasing function होता? क्या step 3, जहां हम inequality maintain रखने के लिए multiply करते हैं, तब भी smoothly work करता? Really think about that, क्योंकि यही small conceptual shifts आपकी true understanding को test करते हैं. Keep analyzing, keep pushing those boundaries, and I'll catch you in the next session.